All right, let's move on to page 2 of the summary. This is about simple linear regression. This is what we covered in units 10 and 11. In this example, we're looking at the relationship between living area and house price. So notice that these are both quantitative variables, right? We're looking at the relationship between two quantitative variables. That's always what we're doing in regression. And we're going to start off by interpreting the output. This is the output that you get from doing analyze fit y by x. Okay, so when we interpret the slope is the predicted change in y for each additional unit of x. So this number that's given right here next to the explanatory variable, that number is the slope. So this is telling us that as living area increases by 1 unit, 1 square foot in this case, that price is expected to increase by $113. The intercept, that's the predicted value of y when x equals 0. So this number right here, it's labeled for you, that's the intercept. So this would be the predicted price when living area equals 0, but that doesn't really make sense. You can't have a living area of 0 and still be a house. So interpretations are not always meaningful for the intercept. Especially if you have predictions that are outside the range of the data. That's called extrapolation, and that's going to be a risky thing to do in general. Okay. For residuals, the formula for a residual is y minus y hat, or you can think about it as the actual value minus the predicted value. And if you look at this on the plot, the ones with the positive residuals, those are the points that are above the line. Right? If the point is above the line, that means that the house's actual price was higher than the line, higher than the predicted price. Whereas the houses below the line, those are negative residuals, and that means that the predicted value was too high for those houses. Okay, so let's move on to some measures of how well the model fits, or in other words, how accurate are your predictions. So correlation is one way to measure the strength of a linear relationship. And to get the correlation, you're going to take the square root of your r squared value. And it could be positive or negative depending on the direction of the relationship. Okay, so here we're going to take the square root of 0.5075. That's the r squared that's given there in the table. And here we see we have a positive trend, right? Higher living area is associated with higher price. So we're going to use a positive number for the correlation. R squared, obviously it's related to correlation, so it measures the same sort of thing. It's measuring how far the points fall from the line. But we can also interpret R squared as the percentage of the variation in y, in this case the percentage of the variation in prices, that can be accounted for or explained based on changes in x. So here we'd say about 50% of the variation in prices can be explained based on living area. And then the root mean square error, or RMSE, that's the typical size of the prediction errors. So here we would say that if we use this model, on average we would be off by a good bit here, 69,104. That's how far off we would expect our predictions to be. Okay, so these are all ways of thinking about how accurate are your predictions. So if the model were giving you very accurate predictions, your correlation would be close to 1 or -1, right? Depending on if it's positive or negative. Your R squared would be close to 1, right? A large proportion of the variability would be explained. And your root mean square error would be small, because on average you would want your prediction errors to be very small. That's what it means to have accurate predictions. Okay? So moving on to inference, the null hypothesis in this scenario is that there's no linear relationship between the variables. No linear relationship between the variables, we should say, in the population. Okay, so we're going to write this in terms of the population slope, in terms of beta 1. The null hypothesis says that the slope is 0, right? So if you think about what it means to say the slope is 0, it's basically saying it doesn't matter what you plug in for x, you're going to get the same predicted value all the way across, right? And then the alternative, generally it's two-sided, that there is a linear relationship in the population. We would write this as beta 1 is not equal to 0. And I do want to point out that when we talk about jump, jump gives two-sided p-values by default. So when you're looking at that fit y by x output, you're looking at a two-sided p-value. Just like any kind of test, we do have conditions that we need to check, and we're going to use residual plots for that. So if we look at a residual plot, so here I'm talking about the plot where I have residuals on the y-axis. What we want to see there is just a random cloud of points around 0, right? We want it to be some over and some underestimating, but no systematic patterns. So this would actually be a good residual plot. Okay? What we don't want to see is some kind of a curved pattern, right? Maybe we see something that looks like this in the residual plot. That would be an indication that the linearity condition has been violated, right? If you have a curved pattern in your residuals, that means that it is not linear. We also don't want to see some kind of a funnel shape, right? Where you have really accurate predictions on one end and then all spread out on the other end. This would be an indication that the constant variance condition has been violated, right? Because the vertical spread is really small down here. You've got really accurate predictions on one end, and it's really big over here. For normality, you can't check normality based on the residual plot, but you can if you look at a histogram of the residuals. And this is when you do plot residuals in JUMP, it gives you the histogram as well. So what we want to see is, roughly normal. So unimodal, symmetric. It doesn't have to be perfect, but we're hoping to see a roughly normal distribution of residuals. What we don't want to see is skew or outliers. So let's go into a little bit more detail to show you where the numbers in the fit y by x output are coming from. So I'm going to be using these numbers down here for slope. Those are the ones we always use. In fact, if you want to mark out the ones for intercept, then you can. So our test statistic for the slope follows the same basic format that we've seen before. This is quantitative data, so this is going to be a t-statistic. And then you're going to put your sample slope, that's your sample statistic. The null hypothesis value is 0, that's what we've been testing. And then divide it by the standard error of the slope. Okay, so if I'm using numbers from the output, the slope we said was 113.12. The standard error, which is listed up there too, is 2.68. And if you divide that, you get 42.17. That's your test statistic. And if you wanted to calculate the p-value, you would be comparing it to a t-distribution with the degrees of freedom n minus 2. So we had up here is our sample size. This is our n. So a really large sample size, 1728. So our degrees of freedom here, this is a t-distribution with degrees of freedom 1726. So a t-distribution with that large degrees of freedom, it's going to go basically to 3 and -3. So 42 is going to be way off the charts over here, 42.17. And technically this would be a two-sided test, so you'd be shading on each side, but it's kind of ridiculous because that's going to be so far out there. If we want to, we can go ahead and put it in the distribution calculator. So this is a t-distribution. Our degrees of freedom was 1726. So you can see about -3 to 3. We can put in our t-statistic, 42.17. Remember, this is a two-sided test. So we're going to put in the negative value here. And not surprisingly, our p-value is tiny, less than 0.0001. So what about the confidence interval? Again, we're going to use this general formula that we've seen before. And we're going to plug in, we're going to do our sample slope plus or minus t star, because this is quantitative data, times the standard error of the slope. So we're going to plug in the slope from the output, 13.12. For t star though, it's really important. We're not using this t statistic from the output. We're going to calculate that critical value in JUMP. So we're still using the t distribution. We've still got the same degrees of freedom, n-2, but we're going to do input probability here, central probability, and if we want a 95% interval, we put in 0.95, and this number would be our t star, 1.9613. All right, so we'll fill it in, 1.9613, that's our critical value, multiply by the standard error, 2.68, and if you put that all together, this would give you your 95% confidence interval.